In this chapter, we will focus on design best practices for modular construction. Modular construction requires a different way of thinking about design. In a conventional project, design development often continues while procurement and field construction are already moving forward. But in a modular project, that approach can create serious problems. The building must be understood early as a product that will be manufactured, transported, lifted, and assembled. This means that design decisions have to support not only the final appearance and function of the building, but also the way the building will move through the factory, arrive on site, and connect with other systems. This chapter introduces 4 core design practices that make modular construction successful: design for manufacturing and assembly, or DFMA, standardization without losing function, disciplined change control, and coordination of interfaces. Together, these practices help the project team protect the main advantages of modular construction: faster delivery, more predictable quality, reduced waste, and better control over cost and schedule. The first major practice is design for manufacturing and assembly, commonly called DFMA. DFMA brings a manufacturing mindset into construction design. It combines 2 related ideas. Design for manufacturing focuses on making building components easier and more economical to fabricate. Design for assembly focuses on making those components easier to install, connect, and inspect. In modular construction, this is extremely important because a module is not just a room or a building component. It is a manufactured product that must pass through several stages: factory fabrication, transportation, lifting, placement, connection, and final inspection. A strong DFMA approach begins by reducing the number of separate parts. Fewer parts usually mean fewer procurement issues, fewer assembly errors, and shorter production cycles. The design should also avoid unnecessary complexity. Complex shapes, unusual details, and extremely tight tolerances should only be used when they are truly needed for performance. Another important concept is poka-yoke, or error proofing. In modular work, this can include self-aligning details, asymmetrical parts, physical guides, or connection points that make incorrect installation difficult. Finally, DFMA should be supported by BIM coordination. Digital models allow the team to test module geometry, MEP routing, connection locations, and assembly logic before production begins. When DFMA is applied well, many construction hours can move from an exposed job site into a controlled factory environment. That shift can improve productivity, quality, safety, and schedule performance. A common misunderstanding about modular construction is that it produces plain, repetitive, or identical buildings, but good modular design does not eliminate variety. Instead, it separates what should be standardized from what can be customized. This is the idea of mass customization. The slide shows an 80-20 logic. About 80% of the building system can be standardized. This may include module size, structural grids, MEP routing, repeated room layouts, and common connection details. These standardized elements allow the factory to work efficiently and repeatedly. At the same time, about 20% of the project can remain customizable. This may include facades, finishes, roof forms, entrance areas, lobbies, public spaces, and selected interior treatments. These elements allow the building to respond to the owner's needs, the site context, and the market identity of the project. The automobile industry provides a useful comparison. Different vehicle models may share the same chassis or powertrain, but they can still have different body styles, interiors, and trim packages. Modular buildings can follow the same logic. The key is to standardize the parts that drive production efficiency while allowing controlled variation in the parts that create architectural identity and user experience. The third design practice is managing design changes. In modular construction, late design changes can be much more damaging than they are in conventional field construction. That means layouts, structural loads, MEP systems, finishes, and major specifications must be resolved much earlier. A seemingly small change, such as moving a sink, shifting a partition, or changing a mechanical chase, can have a major impact. It may require new shop drawings, disrupt material orders, stop the production line, or even force completed modules to be modified. For this reason, modular projects need strong design discipline. First, the team needs early stakeholder alignment. The owner, architect, engineers, general contractor, and modular manufacturer should collaborate during the concept phase, not after the design is already complete. Second, the team should use prototypes and mock-ups. A full-scale module mock-up allows the owner and design team to review clearances, finishes, fixtures, lighting, and maintenance access before mass production begins. Third, the project needs a clear design freeze. At that point, layouts, loads, specifications, and key systems are formally locked. Any later change should go through a strict review process to evaluate cost, schedule, procurement, and production impacts. The main message is simple: modular construction rewards early decisions and punishes late uncertainty. The fourth major design practice is interface coordination. A modular building is assembled from large three-dimensional units. These units must connect accurately to the foundation, to adjacent modules, to the building envelope, and to shared MEP systems. The biggest technical challenge is tolerance management. Factory-built modules can be produced with very tight tolerances because they are built with controlled equipment, jigs, and fixtures, but site-built foundations often have looser tolerances. Modules may also flex slightly during transportation, lifting, and placement. If these differences are not considered during design, modules may not align correctly on site. Misalignment can lead to racking, structural stress, damaged finishes, leaks, poor acoustic performance, or installation delays. Designers should therefore provide practical adjustment strategies. These may include adjustable plates, slotted holes, shims, alignment cones, and flexible connections. Interface coordination also includes MEP integration. Pipes, conduits, ducts, and equipment should connect in accessible locations, such as corridor ceilings or vertical shafts, so field crews can complete the work efficiently. Fire and acoustic sealing are also critical. Mate line joints between modules must be sealed properly to prevent the passage of smoke, fire, water, air, and sound. Finally, facade and finish stitching must be planned carefully. Some finishes may be intentionally left incomplete in the factory, so they can be applied continuously across module joints on site. This helps the completed building look seamless rather than assembled from separate boxes. The Citizen M Hotel in Seattle provides a clear example of modular design best practices in action. This project was Seattle's first modular hotel. It is a 10-story building with 264 guest rooms, assembled from 228 factory-built volumetric modules. The modules were manufactured off-site by Polcom and delivered substantially complete, including bathrooms, bed frames, smart controls, mirrors, blackout blinds, and other room components. This project shows the value of DFMA. Because the guest rooms were highly repeatable, the factory could integrate room construction, furniture, and technology installation into an efficient production process. It also demonstrates the 80-20 approach to standardization. The guest room modules were standardized to support factory efficiency, but the public areas and exterior facade were customized to create a distinctive hotel identity. The bold facade and public spaces helped the building avoid looking generic. The project also benefited from design freeze discipline and parallel scheduling. While the concrete podium was being constructed on site, the modules were being produced off-site. This required early coordination and strong control of design decisions. When the modules arrived, the team was able to set approximately 7 to 8 modules per day. The 228 modules were stacked in only 89 days, and the overall schedule was shortened by about 4 months compared with conventional construction. The project also supported sustainability goals by reducing waste and achieving LEED Gold certification. Overall, the Citizen M Hotel shows how DFMA, standardization, change control, and interface coordination can work together to make modular construction faster, more predictable, and more efficient.